Hey everybody, I hope you can hear me okay. I need to purchase a microphone for this document camera if I'm going to do this kind of recording. I'll try and speak up, but you might want to turn the volume up on your device. Let's work through example 1 together. Let's look at the topic of motion through a numerical approach. And guys, all that means is a numerical approach is that you're given a data table. You're given data, information. All right, so we have this object that's moving along the x-axis. This object is moving left and right, maybe left and right, maybe stops for a while. And what we're given is we're given velocity values. So let's kind of look at the data table and look at the units of measure. The time is measured in minutes, and so these are the only time at which we have data, that we've collected data, velocity of this object. I notice the velocity is given in meters per minute, so all good things to kind of pay attention to. All right, these are our velocity values, and it also tells us that this velocity function is differentiable. That's pretty important. If we know a function is differentiable, then we also know that the graph is continuous. And I would recommend that if I were you and you're struggling on something like this, that this is a manageable number of data points. I mean, look, there's 1, 2, 3, 4, 5, 6 ordered pairs. How easy would it be to take a few seconds and plot these on a grid? Look at the time values anyway. They're all in the first quadrant. Okay, so it might be very revealing to you guys if you were to produce a graph. Okay, a lot of things can jump off at the page at you guys if you do have these plotted. Let's look at question 1. At time equals 0, is the particle moving to the right or to the left? Well, notice the time right here is 0. Look at the velocity value. Well, we've already seen that if the velocity of an object is negative, and this object is either moving left or right on the x-axis, that a negative velocity corresponds to moving to the left. But notice here that it also says explain your answer. All right, so there's two components to this, the right answer and the explanation of why you chose that. So we're just going to practice good sentence structure. We're going to take the question and make it our answer. And what I mean by that is, let's just address the question. Let's make a really polished answer. We know the particle or the object, whatever, is moving left. We certainly would get credit for addressing the question correctly and getting the right answer, but let's explain our answer. The particle is moving left because the velocity at time equals 0, that's your input, velocity of 0, is equal to a negative number. It's equal to -3, and this means that that's less than 0. Okay, so let's just make sure, in case you have any questions, do I have to put v of 0 equals -3 is less than 0? Do I have to have all this? No. This is acceptable as well. V of 0, the velocity at 0 seconds, is less than 0. Because they gave me the value of -3, I don't have to spit it back to them, although that's probably a good thing. You're done. You got the right answer, and you've explained it. Could I have used words instead of symbols? You know, could I have said, well, the particle is moving left because the velocity at time equals 0 is -3, which is less than 0. Yeah, they're going to take your words. Okay, explain your answer could mean words or it could mean symbols. So that's a very common thing that you'll see on an AP test that's a free response question. Explain your answer means you can either do it with symbols or words. Question 2, is there a time during the time interval from time equals 0 to 12 minutes when the particle is at rest? Explain your answer. You might remember from worksheet number 1 that a particle is at rest when the velocity is equal to 0. It's pausing, it's thinking, you know, it's resting, it's catching its breath. Look at the data table. I don't see any 0 values for velocity. That's the first thing I look for. But then I dig deeper and I look. I look at the velocity values and I see that they go from negative at time equals 0. My velocity is negative, but the next time data is collected, 2 seconds later, my velocity is positive 2. Well, if you were to plot these points, it's easy to see that this y value is negative, this one's positive. I would have had to have gone through the velocity, the x-axis, the time axis, if you will. Okay, so yeah, this particle's got to be at rest. Is there another time at which I might have passed through the x-axis as indicated by the data? No, because it looks like all these velocity values remain positive. That's not to say that perhaps between 2 and 5 seconds, maybe the velocity did go to negative and then back to positive, but I don't know that. I can't know that from just the selected values. I can't make up things. So I only see that the signs change on the velocity values one time, from 0 to 2 seconds. So let's respond to that question. Yes, the particle is at rest sometime between time equals 0 and time equals 2 minutes. So we answered the question, now let's explain. Because the velocity, v of t, changes from negative to positive. Think about that. If your velocities change from negative to positive, that means that if you're traveling on a straight line, you're going from moving to the left and then having to turn around and go back to the right to get to a positive velocity. Well, if I'm traveling to the left and have to turn around, I'm going to have to pause to turn around. That's an adequate justification. Something else that you could think about, since we've just been looking at theorems, is this. What if you put, I'm just giving you different options as far as responding to explain your answer. What if you would have put because, and instead of all of this, because of the IVT, intermediate value theorem. Well, we've just been studying that, and what that means is that I have to pass through every y value, so between -3 and 2, if I have a continuous function. And I do have a continuous function. More specifically, I have a differentiable function, but this graph is connected. It's continuous from -3 to 2. So I'm going to have a y value, every y value from -3 to 2, so that does imply that I would pass through 0. You may be thinking of another justification, and if you do, please share it with me, and we'll see if that would work as well. Right. Use data from the table to find an approximation for v prime of 10. Okay, we want an approximation for the slope of the velocity at 10. Okay, so an approximation for the rate of change at time equals 10. Well, I don't have an equation that I can differentiate. I don't know what velocity is equal to as far as an equation. If I did, I'd find the derivative and plug in 10. At best right now, since I don't have an equation, the only thing I can do is approximate it. So I'm going to look at my data table. I'm going to find 10. Okay, so 10 is going to fall between 8 and 12, and pretty convenient, it falls right in the middle between 8 and 12. I want to estimate the slope of the graph at 10. Well, again, my suggestion is, if you don't understand what's being asked, is to plot these points right here. Okay, and real quickly, I'm going to draw a sketch of it so we can get a visual of what I'm supposed to be estimating. I'm only going to label the input values that I've given so that I make sure that I don't make up anything that I don't have. All right, a quick plot of the graph. It's continuous and differentiable. I just don't know the concavity. I don't know what's happening in between the points. So, you know, it's just going to be an estimate of what's going on here. I certainly want it to be a function, so let me fix that. All right, let's estimate the slope of the graph at 10. Well, here's 8, here's 12, here's 10. Okay, well, all I can say is that on my graph right now, it appears that the slope, if I looked at that point at 10, okay, it appears that the slope of the graph is negative. It appears that, you know, we have a negative rate of change because velocity is decreasing. Okay, that's what it appears to be doing. Again, it could be doing other things. The graph could have fallen down and gone back up and then back down here. I'm not certain. All I can do is estimate the slope of the graph. So, and to estimate, I choose data points. 10 falls between the time 8 and 12, so let's use those two ordered pairs. So what I'm going to do is I'm going to do a delta y over delta x with these two ordered pairs. Right? So the way I'm going to denote that, or note that, is I'm going to put b prime of 10 approximately, so the average rate of change is what I'm going to be using to approximate the instantaneous rate of change at 10. So it looks like this: v of 12 minus v of 8 over 12 minus 8. Show the computations that lead to your answer and indicate units of measure. This is the work. Now look at the units of velocity. I'm going to put them up here. Meters per minute. And the units of the input values are minutes. Okay, so it's as easy as stealing the y and the x units. I'm going to steal the units here in the table and steal the units here. I'll get that point right there. So v prime of 10 is approximately 5 minus 7 over 12 minus 8. Negative 1/2 meter per minute every minute. Looking back at the question here, it says use data from the table to find an approximation. Did it? Explain the meaning of v prime of 10 in terms of the motion of the particle. I have that yet to do. Show the computations and indicate units of measure. I did that. Let's go back to explain the meaning of v prime of 10 in the context of the problem. The prime notation indicates a rate of change. So v prime of 10 means the rate of change of the velocity at t equals 10 minutes. That's the input. Okay, and we want to indicate the units of measure for the answer. So v prime of 10 means it's a rate of change, because of the notation here, of the velocity at time equals 10 minutes in, and I just want to get the units, meters per minute per minute. If you wanted to say that was the acceleration, means the acceleration of the particle at time equals 10 minutes, that would have been accepted too. Okay? But that notation can be easily translated into it's a rate of change, because of the prime, of what context, the velocity, at what particular time. So the important things here are the input value here, 10, what does that mean, time, and the output, what would the answer have as units. Okay? Or you could say it's the acceleration at time equals 10 minutes in meters per minute every minute. So the particle is the particle's acceleration at time equals 10 minutes is negative 1/2 meters per minute every minute. That would be acceptable too. Okay, what are some other questions they might ask about for us that we've learned so far and how we can respond to it? It says let a of t denote the acceleration of the particle at time t. Well, we know acceleration is the derivative of velocity. Is there guaranteed to be a time in the interval from 0 to 12 such that the acceleration, the slope of velocity, is equal to 0? Justify your answer. All right, so is the slope ever 0? Is the slope here on this velocity graph ever going to be equal to 0? Will the slope ever be 0? Oh, certainly. You can look at the graph, you can look at the data table. Okay, so let's take the question and make it our answer yes. There is a time t equals c in the given time interval such that a of c is equal to 0 because, okay, will I ever have a 0 slope? Well, that's the same thing as asking, do I have any mins or maxes, relative mins or maxes on my graph here? Well, we certainly can see that I'm going to have to at least have one time where my slope of this graph, my acceleration, is 0, because we see that the velocity values are increasing and then they start to decrease. So if this graph is increasing, changing to decreasing, I'm going to have a maximum because the slopes are going to go from positive to negative. Okay, so the slopes of this graph are going to go from positive to negative. Another way to think about it is the y values, okay, of the velocity function change from increasing to decreasing. So we can use that argument too. So we're going to say because v of t, these y values, change, it changes from increasing to decreasing. And I would go ahead and further say, and the mean value theorem would apply because v of t is differentiable. And why is that important? Why is it important that we say that the velocity graph is differentiable for this question? They're wanting us to find out if the acceleration is ever equal to 0. If this function wasn't differentiable, I could draw sharp turns. So right here, that wouldn't be a 0 slope, that would be a does not exist slope. Okay, so that's one way to respond. Another argument without having to use the mean value theorem is to say, or, back up here, because v prime of t changes from positive to negative. Just means the slope of the velocity graph changes from positive to negative. And that's just another way to say that the velocity graph itself changes from rising to falling, increasing to decreasing. So this would have been acceptable too. You could have avoided the mean value theorem as long as you somehow indicate that the velocity graph is increasing and goes to decreasing, and it's differentiable. Okay, you would get the point there. Okay, or you can say that the slopes change from positive to negative, indicating on this differentiable function that you have a relative extremo, which is a zero slope too there. All right, so hopefully that's a good example for some of the questions that are going to come up on example 2 and 3. And then also, if I didn't mention on example 3, we can forget about this problem. We'll do that at a later date.